Good afternoon. I'm Chuck Hammock with Andrews, Hammock & Powell. Today we're going to do our fifth in a series of six live webinars related to underground thermal energy storage. This is all part of a technology transfer project that we are doing for the Department of Defense under their ESTCP program. Today's topic is going to be on test and balancing and commissioning of geothermal heat pump systems in general, and we're going to get into some of the particulars of underground thermal energy storage also, which is the type of projects we've been demonstrating for the Department of Defense. I'm a mechanical engineer with Andrews, Hammock & Powell, and the principal investigator on this technology transfer project. And Brandon Caves, who you'll meet in just a moment, is the co-PI on the project. We both work together designing and installing. We don't actually do the installation, but we do the commissioning and tab of these geothermal heat pump systems we've done for DoD. So that's a little bit about who we are and who I am. Brandon, can you introduce yourself?
Yeah, sure. Hey, good afternoon, everybody. I'm Brandon Caves, also work here at Andrews, Hammock & Powell. I'm the head of the Commissioning and Test and Balance Department, but I'm also highly involved in the Geothermal Department. And in my 10 years here, I have been highly involved in commissioning and testing and balancing of all sorts of HVAC systems, but also geothermal systems, including open loop, closed loop, and underground thermal energy storage systems. So that's kind of what we're going to talk about today. And I will jump right into this presentation. So Chuck's already talked about some acknowledgments, but I just want to hit them again. We want to thank DoD and ESTCP for funding the original UDIS demonstrations and this technology transfer project. We want to thank MCLB in Albany, Georgia and Fort Benning, Georgia, and their personnel for hosting the original BTES and ATIS demonstrations respectively. We've talked about those demonstrations in our other webinars if you've been following along. We also want to thank ASHRAE for listing this webinar in their national newsletter. It's been a great help and has really gotten the word out about these things. So our outline today is we're going to talk about what TAB is. What does it stand for? What does it mean? What is commissioning? We're going to talk a little bit about technical versus process commissioning, the difference in those two, test and balance of geothermal and underground thermal energy storage systems. We're going to talk about key tab and commissioning items to get maximum performance out of your systems. We're going to talk a little bit about monitoring and verifying performance and problem solving, and also general installation inspections for your geothermal heat exchanger. And then we'll have conclusion and Q&A at the end, and you'll also be given a chance to get a PDH for this. So what is TAB? So TAB, if you've heard people talk about that, stands for testing, adjusting, and balancing. It's adjusting and balancing the flow rates to design conditions. That can be air or hydronics. The test and balance contractor is to test the systems fully. And when he tests the systems fully, he uncovers a lot of problems just inherently in that process. He'll record the data, and he compares the data to what the designer specified. Air and water flow rates is some of the things that he records, as well as temperatures, dry bulb and wet bulb entering and leaving all of the coils. Other things he would record would be amps and volts from motors, along with other data and nameplate data. So the process of recording all this data, like we said, will just inherently uncover a lot of the problems because it requires the tab technician to run the equipment and the systems through the various modes of operation. What is commissioning? Commissioning is the quality assurance process to assure that sustainable and energy efficient systems achieve the owner's project requirements as specified by the design team. It also assures that the specified systems are installed correctly and in a workmanlike manner by the construction team, And it's also to help the facility managers understand the purpose of the building system's operation and maintenance requirements. So this enables the facility to provide the desired environment, meeting the owner's project requirements for the foreseeable future. Commissioning, I like to say this, it's just making the stuff work. I mean, that's kind of what it used to be called when the test and balance contractors were ultimately responsible for commissioning. It's just making the stuff work. And making sure that the systems operate as a whole. Commissioning is not just showing up the day after substantial completion on a project and pressing the big red easy button. That's not what commissioning is at all. Unfortunately, commissioning has gotten a bad name on some projects because contractors are used to seeing a commissioning agent come in after the systems have been started up, and maybe even, like this is, after substantial completion. They come in, they make a walkthrough, they fill out some paperwork, and they leave. To me, that's not commissioning at all. Commissioning in our world is a very hands-on approach, and it's testing each piece of equipment in depth to make sure it's performing, and it is testing the entire sequence of operation to make sure the building as a whole operates as it should. So let's talk about NEBB certification. What is NEBB? You may have seen this in project specifications before in the test and balance spec. NEBB used to stand for the National Environmental Balancing Bureau. It was established in 1971, but since then they have reestablished their name simply as NEBB or NEBB. NEBB is the leading accrediting authority and certifying association for several HVAC-related professional disciplines. AH&P holds NEBB certification in the following disciplines: commissioning, which we call whole building technical commissioning of new construction. That's what NEBB calls it. And then retro commissioning, which would be commissioning of existing systems to get them back up to snuff. And then also testing, adjusting, and balancing of environmental systems or just simply HVAC systems. There are other organizations out there that are very reputable, like the Associated Air Balance Council. They're pretty much known just as AABC, and we keep NEBB and AABC in most of our project specifications, and we highly recommend either of those agencies. We recommend that your test and balance or your commissioning agent be certified by one of those two, or another reputable one. So let's talk about technical commissioning versus process commissioning. We touched on what commissioning is not, and commissioning really is not process commissioning. Process commissioning is just really a bunch of paperwork, in my opinion. It's going through the process. It is pushing a bunch of paperwork around and not really putting your hands on anything. It involves a lot of sampling strategies, and it's just, in our opinion, is not a good way to do things. Technical commissioning, on the other hand, is more than just paperwork. It is a very hands-on approach of testing each piece of equipment, like we said previously, and especially with controls, verifying the entire sequence of operation. So it also doesn't allow any sampling strategies. So we feel like every piece of equipment needs to be tested. For the most part, things like grills, if you're verifying grills, we do some sampling strategies on that. But as far as testing the mechanical equipment, we don't believe sampling strategy is a good approach. NEBB doesn't allow process commissioning. They only allow technical commissioning. So let's talk about TAB of geothermal and UTIS systems, underground thermal energy storage systems. So some key TAB items for maximum performance would be the hydronic balance of the ground loop heat exchanger. That's kind of an important thing, and maybe even some TAB contractors may not be very familiar with that. If the bore field has different sections, these sections should be balanced equally. Or utilize reverse. If the designer has utilized reverse return, then it's set up for automatic balancing, and we'll cover that in a little bit. Also, proper balancing of an open loop ATIS system. So how in the world do you balance an open loop system? There's ways to do that, and we're going to cover that. Another key tab item that some balance contractors may not think of has to do with the dry coolers on a UTIS system. We've talked about dry coolers in our previous webinars, and some dry coolers that we've run across have different things for energy savings, for like low capacity motor management, which is known as LCMM, and that allows the fans to stage on and off and speed up and slow down to meet the load. Sometimes dry coolers that we've seen don't have that enabled, but it is available, and it's just something that has to be set up by somebody, and most of the time that somebody needs to be the tab guy. Pumps, minimum and maximum VFD speed, that's something the tab contractor has to set up, especially with submersible pumps. Submersible pumps are a little different. We'll talk about that later on too. They're a little different than traditional centrifugal pumps that are in suction or inline pumps, in that they can't turn down to 25 or 30%. They can only turn down to 50%. So if a tab contractor doesn't know that, he needs to be aware of that. We'll talk about dynamic reset strategy for pumps, how we're going to dynamically reset the pump differential pressure set point. That's for hot or chill water application, or even loop water application. And then fan speed would be the same thing. The tab contractor can help dynamically reset or implement a dynamic reset strategy for the air systems, which would reset the static pressure set point for the fan to meet the load of the building, to keep the fans from running too fast. We don't want them to run any faster than they have to. And then the tab contractor, another very important job of his is to measure the outside air intake. That includes energy recovery units and dedicated outside air systems. So let's start off with reverse return systems. What are they? How do they work? And how do you balance them? Well, a reverse return system actually doesn't require any balancing of these circuits. We'll call them sub-circuits. And they wouldn't require a manifold vault to house all the balancing valves. If you had a traditional geothermal heat exchanger, you would need a vault. You need somewhere for all the balancing valves to be. Well, if you design your system with a reverse return, you don't need the vault, unless you just want the vault for isolation purposes. Then by all means, there's nothing wrong with the vault. But in this drawing here, this is actually a drawing of a Borehole Thermal Energy Storage GHX that we've probably shown in previous webinars. This was at MCLB Albany, and this was designed with a reverse return configuration. And this water in this path that I've highlighted here can flow in either direction. It's reversible, but let's pretend for the moment that the water is flowing from left to right, starting on the red there. And if you'll bear with me just a second, I'm going to try to get a laser. That is not what I wanted. I'm sorry. Pointer options. Laser pointer. There we go. Okay, so hopefully y'all can see my pointer a little better now. So our water's coming in here on the red, and it hits this first circuit here. We're going to call these sub-circuits. And this area right here is called a trisector in our design. We had 3 trisectors, and each trisector had several sub-circuits. So this is just one trisector here, and we hit the first trisector first. Our supply comes in, hits the first trisector. Well, when it hits the return main, it is the last sub-main to hit the return main. So it's the first one to leave, but it's the last one to be picked up by the return. In the same way, the second sub-circuit would be the second one to come off of the supply main, but it's the second from the last to hit the return main. So essentially what you end up with is each one of these sub-circuits has the exact same length of pipe is the exact same distance away from the pump. So typically the circuits that are closer to the pump gets the most flow, and the ones that are farthest away from the pump gets the least flow. With this configuration, each circuit is the same distance away from the pump and has very close to the same pressure drop. Each circuit has the same pressure drop overall, pretty much. We actually, on this project, we took a ultrasonic flow meter while all of this was uncovered, and we measured the flow rate through each submain in all three trisectors and compared to the total flow of each trisector. And believe it or not, this actually works. Each of these submains were plus or minus 10%, I'm going to say, to be in the same flow rate. I'd always been told that they were self-balancing, but that was actually the proof in the pudding. And so we think this is a really good way to do it. Requires no manual balancing. Our next slide here shows a traditional GHX without reverse return, and this does require manual balancing. Nothing wrong with this design at all. It's a good way to do it. It actually gives you some access. Over here we have these vaults. We have a core vault, and in our core vault we have a bunch of isolation valves. We have two perimeter vaults where our balancing valves are. So our water is coming in. Remember, it can flow either way, but just for discussion purposes, we're going to pretend it's flowing this way in the direction of my pointer. Hits the core vault first, is distributed to all these circuits. Each one of these circuits goes through the three boreholes in series, hits the perimeter vault where our balancing valves are, comes back on the return, and heads back out to the building. So in this design, you have to have a tab contractor go down in each of these vaults and balance these manual balancing valves. And it's very typical of what a tab contractor would do, nothing that they would be unfamiliar with. One thing I do want to mention is that in these vaults, if you're designing this, you have to design these manual balancing valves to be bidirectional. And there are a few balancing valves that have those capabilities, but you do want to ensure they are bidirectional. So a tab contractor's responsibility on a geothermal project is not limited to just the exterior stuff, the GHX or the dry coolers. He's also got a lot of work to do inside the building. And in this drawing here, this is very typical of what you would see on a geothermal project where you have water source heat pumps. In this system, we have water source heat pumps, and you can pretend that the GHX is out here somewhere, but this is just the building loop. Most of the time on water source heat pumps, you end up with a two-position control valve because we don't need it to be modulating. We just need it to be on or off. Another thing designers do a lot of times on water source heat pumps is they install these things called auto flow balancing valves, or sometimes they might specify a pressure-independent balancing valve. Both of those are really good ways to balance water flow on a water source heat pump job, because when we need the water source heat pump, the control valve opens up, and in our system here, each of these water source heat pumps need 10 GPM, and this auto flow, you would order it for 10 GPM, and it just flows 10 GPM. And the way you verify that is you measure the differential pressure across this valve on two little ports here, and if your differential pressure is anywhere between 2 and 32 psid, those numbers can vary a little bit per manufacturer, per valve, but on the valves that we use a lot, 2 to 32 psid, you know that you have 10 gallons a minute. So in a sense, the system is self-balancing. However, you still need a tab contractor to go through here and verify that you're not out of range. If you are out of range, then the pump is either running too fast or too slow. So pretend the tab contractor comes through here and he measures everything, and everything is 2 to 32. But this very remote valve out here, the one that's farthest away from the pump, is, instead of 2 psi, pretend it's 5 psi. In that case, your pump is running too fast. And this differential pressure that is measured right here by this transducer is sending a signal to a controller, and the controller is going to the pump. In that case, you would need to lower your differential pressure set point. You would lower that set point until the VFD slows its pump down until you get very close to 2 psi on your most remote circuit. That would indicate that this valve is fully open and your pump is running no faster than it absolutely has to. That is kind of the definition of a system being balanced. A system is properly balanced when all your flow rates are proportional, and also when you have at least one fully open balancing valve in the system. So at 2 psi, this balancing valve is 100% open. So like I said earlier, you would slow the VFD down until you get 2 psi at your most remote water source heat pump, and then you would look at your differential pressure here, and that would be your set point. So your tab contractor is the guy that's responsible for telling the control contractor what the differential pressure set point is. So your tab contractor needs to know how to do this. Very important that we don't run that pump any faster than we have to, just waste horsepower and waste money. This is also a system that you would typically see used in geothermal. This is a chill water system. You could have this could be a modular chiller that uses groundwater or water from your GHX out here from your BTES or your ATIS. In this case, like I said, we have a chill water loop. We have chill water coils here. We have modulating control valves instead of two-position control valves, because we want to be able to vary the capacity through the chill water coil. And anytime we have modulating control valves, we really don't want automatic balancing valves. We want them to be manual, because we don't want these automatic balancing valves to be throttling back and closing down and opening up, and it just ends up fighting this modulating control valve. So really you want manual balancing valves here. You want your tab contractor to come and set these up so they're proportional, and they're just fixed after that point. So the purpose of this slide is your balancing contractor not only has to balance these valves, again, he has to tell the tab contractor what differential set point to use. So he balances everything at 100% flow. He looks at the differential pressure transmitter. He sees that he has 10 psi. He tells Mr. Control Contractor, I need a 10 psi set point, and the control contractor programs it in, and that controls the pump, and everybody's happy. What can happen sometimes on chill water systems is that you can get to a point where all of these valves are throttled and we have no open valves anymore. At that point, our system is really not operating as efficiently as it could. The pump is running too fast. Even though it may be hitting set point, it's running too fast. So what the control contractor can do is he can reset the differential pressure set point. We pretended it was 10 psi. He can reset it down to 9 and then wait and let's see what happens. So he resets it at 9. The pump slows down. We got less water flow now. Eventually, these valves will start to open up because the space may be getting hot because it's getting less water. And you want to keep resetting that set point down until at least one of these valves is fully open. Now, we really don't want it to be fully open because we don't want to run the risk of underflowing the coil. So we like to say 95% open. So when one valve gets to be at least 95% open, we stop. We stop resetting the set point and we wait and see what happens. If more valves start to open up, or if this one goes to 100%, then we could always reset our set point back up, which would cause the valves to throttle back down slightly. So again, we don't want to run this pump any harder than we have to. Reduced pressure equals reduced operating costs. Yeah, I do want to remind everybody to please submit your questions via the chat on YouTube Live. You can submit your questions anytime during this webinar. Joey is monitoring those questions, and we will, Joey or Chuck is, and we will address all those questions at the end. So I'd love to hear your questions, and just shoot them at us when you get ready. So we've talked a little bit about balancing closed loop systems. Let's talk about how do you balance an open loop system, such as an ATIS system, Aquifer Thermal Energy Storage. How do we ensure that the total flow rate of the system is evenly injected into the wells? Just as a refresher from our last webinars, this is an ATIS system in Pensacola, and we're currently designing this. We have 3 cold wells here, and here are 4 buildings. So this is on a pretty large scale. 4 big barracks buildings, 3 cold wells here, 3 warm wells over here. So in the cooling mode, we're pulling cold water out here, and we're running it through our buildings, and our buildings are adding heat, and then we inject that warmer water down into the warm wells. Well, how do we ensure that this total flow rate gets injected evenly? We don't want to inject it all into one, because this project is, like I said, in Pensacola, Florida. We're just a few hundred yards from the ocean, and the static water level, groundwater level, is only 7 feet below grade. It's not very far down. So we don't want to mound up the water in here any more than we absolutely have to. So we don't want to dump it all down into one. We want to split it. So we're going to talk about how we do that. So the way we've done it is we use an injection valve, which we've covered in previous webinars, and we use this injection valve to do 2 things: to control pressure and to control max flow. And doing those 2 things, most of the time we can get that flow evenly split. So here is a diagram of our well. Here's our well casing coming up from below grade. Here's our horizontal ATIS pipe, which is bidirectional. We have a water meter in here. That water can only flow one way through, so we have to have this bypass. When we're extracting water out of the well, we would bypass around the flow meter and go out. But when we're injecting, we're just going straight through the flow meter, and we're going down the well. We also have a pressure transmitter here. This pressure transmitter goes all the way up here to this valve controller, this injection valve controller, which is shown here. This is these 2 devices here. This is the controller, and this is another little small controller that's a little subcontroller. But they're both mounted on a backboard above grade. These 2 devices here are mounted in our enclosure, in our pit down here. This is actually an HDPE vault. This box contains a small little hydraulic pump. We like to call it a coffee pump, because I think it may be very close to what they put in Keurig coffee makers. This has distilled water in it. It's just a reservoir open to atmosphere. These 2 devices are installed down here in the pit, and they receive a signal from the controllers up top. We also have a water level transmitter that goes down the well here and is connected all the way back up here to the controller, so we know the level in the well. So this device allows us to control our injection valve, and I'll show you what we do with that. Here's our injection valve that is down in the well. The pump will be sitting down here. The injection valve screws right onto the top of the pump. So in pumping mode, the injection valve is closed. We have 2 tubes that I forgot to mention in the last slide, but the tubes come from the coffee pump. It's a high pressure and a low pressure. Here's our little coffee pump in this diagram. So when this pump is off, the pressure is equal on both sides of these tubes. It's just static pressure from this reservoir. Well, when we go into pumping mode, Now our little coffee pump turns on and applies high pressure to one side of this regulating pressure side. So high pressure comes in here. The other side is still just seeing static pressure from the reservoir, and the differential pressure presses against this seat and compresses that spring and allows this valve to open. Any other time the spring keeps the valve closed. So that's kind of how the injection valve regulates water flow to maintain pressure, the pressure set point, and the maximum flow set point. So, like I said, we have two set points. We have a maximum pressure, maximum flow. We have to figure out what we want our pressure set point to be. This is how we do that. Is that here? This is a different job actually. So there's only 4 wells instead of 6, but each one of these wells, each one of these pits are at different elevations because they're a long way away, and this job was not good and flat like Pensacola. But we know the elevation of our highest pipe in the system, and we want to keep 5 psi up here to keep from our system going to negative pressure to prevent oxygenation of the water and outgassing of oxygen and of dissolved oxygen, and we don't want to cause any iron fouling if we have iron in the water. So we want to keep it positively pressurized, so we can easily determine from the height of our pressure transducer to our highest pipe. We can measure that. And then we need a survey instrument such as a building level to measure the elevation difference between these two. Now we can calculate what this pressure, what the height of this, and the height of this one, and the height of this one. So essentially each one of these wells, the valve controller, the injection valve controller, has to have a different pressure set point in order to make the valves all control to the same set point so that they get the same amount of flow rate. The other set point that we have is max flow. So we tell our controller, hey, we don't want you to go over 500 gallons a minute. If you go over 500 gallons a minute, start closing down. As you can see, this little diagram here shows both flow and pressure set point and flow set point. Our max flow set point is up here, and we have a hysteresis here that you have to program in. If the flow rate gets above that hysteresis, the PID comes on and it starts counting to see what the rate of increase in flow rate is. Once it breaks the maximum flow set point, the valve starts closing based on the PID having been counting for this whole period, and it gets it back under control. Same way with the pressure set point down here. If we drop too low, then we have to close our valve down to get the pressure back up. We don't care if we're too high. That's okay. We just don't want to drop below our pressure set point. Anytime the valve closes, our pump is going to have to speed up because the pump is reacting to the needs of the building, not the needs of pressure or flow rate at the individual well, but the building overall. So our pump will react to those changes. So that helps to keep our flow equal for the most part. In this diagram, this shows the project in Pensacola. Our cold wells would have been down here somewhere, and these are our warm wells, and at max flow, we're at 1,479 gallons per minute. And we're splitting that 3 ways, and we're injecting 493 gallons a minute into each well, and everybody's happy because it's balanced. But we have still run into problems with this, and we're just being completely honest here, is that we're still working through some problems. The problems that we've encountered are when the building goes into minimum flow, when it's springtime or fall or winter, and it doesn't need very much cooling or heating. In this scenario, let's pretend we're at minimum flow, which is just one of these cold wells pumping, and that pump is running at 50%. So now our system flow rate is 247 gallons a minute. Well, ideally, we'd want 82 to go here, and 82 to go here, and 82 to go here. But one well can easily accept 493 with no problem. So we know it can take 247. So what we've seen happen is when the system reverses, when it changes direction from charging mode to discharging, from cooling to heating, however you want to talk about it, when this flow direction changes, then all these injection valves automatically start trying to get control. Well, one of them ends up getting control faster because it can take the whole 247. And so it just sits along there. It's sitting there and it's happy and it's getting all the flow rate, and these other guys are not getting anything. One way that we have that we're working through right now to try to eliminate this problem is to get a writable set point for max flow in the injection valve controller. We're going to try that on Pensacola, and if we gave it in other words, if that maximum flow set point was able to be written to constantly by the BAS system, and say, okay, we know our system flow rate is 247. We want to give this a max flow set point of 82. Now all of a sudden, it can't go over 82 without that valve starting to throttle back. Once that valve throttles back, it sends more water over here, and that should balance the system back out. But just to let everybody know, we have struggled with balancing of these systems at lower flow rates. At the max flow or at the design flow, it's no issue. But the farther you get down toward the minimum flow, the less out of balance it seems to get. Key commissioning items for maximum performance. Frequent site visits. Don't settle for minimum site visits that only happen at the end of the project. That's no good. It's difficult to know if the systems are being installed correctly without multiple site visits. And sometimes just show up unannounced. That's beneficial to ensure your observations are truly representative of the normal day-to-day installation procedures. When you go on site, if you're the commissioning agent, take borehole depth measurements. You can collect grout samples. You can observe the HDPE welds. And you can do that periodically throughout the construction of the GHX. Grout thermal conductivity. While you're there, you're looking at the project, take some grout samples. Ideally, multiple samples. You could even do multiple samples per borehole to make sure the batches are being correctly mixed between batches. And here's a picture of our meter that we use to measure thermal conductivity. We would simply grab some samples, put them in a cup, bring them back to our office, let them acclimate to temperature, to room temperature, and then we would test them, and we would see if they meet spec, if they meet our spec or the spec of the project. Here's an example of our thermal conductivity testing report for grout. We use the Therm Test TLS 100, which we had in the previous slide, and we also use the testing standard ASTM D5334-14 standard test method for determination of thermal conductivity in soil and soft rock by thermal needle probe procedure. So this is kind of what our test report would look like. Another good thing for commissioning agents to do is to verify proper flush and purge techniques through the GHX. AH&P recommends a minimum of 4 feet per second through the entire system, no matter the pipe size. So the tools that we would use to ensure proper flushing and purging would be an ultrasonic meter shown over here, also a differential pressure hydrometer that you could plug into the flushing pump and make sure your total flow is correct, or if you had a Venturi flow meter, you could plug in there and determine flow rate. But just anything to determine flow rate. On this particular project, we used our ultrasonic flow meter a lot. We actually went to every single one of those submains and made sure we had 4 feet per second. We made sure we had 4 feet per second through the larger pipe, all the way back, every different pipe size. In this particular picture, we have a frac tank over here, which is just an open loop tank. I actually think it's out of the picture. I think this is actually storage container here, but there's a frac tank over here and a pump. The pump pulls water out of the frac tank, circulates it through the system at a minimum of 4 feet per second, dumps it back into the top of the frac tank where all the beer cans and cigarette butts and air bubbles and everything else that got left in there was separated. And so we were there for all of that, and we made sure all that happened correctly. We also like to perform and verify the ASTM compliant pressure test of the system. So this is the contractor pressure testing the whole system. And HDP is a little different than steel pipe. It stretches when heated, when out in the sun, and it actually stretches just when you apply pressure. So we wanted to make sure that there's a procedure for testing HDP. You want to make sure the procedure happened correctly. So what we did is we installed a pressure transducer here and a flow switch, just a flow switch like you'd have on your well at home if you're on a water well system for your drinking water. And there was a hydrostatic pump connected to the system back here to keep it pressurized. So the hydrostatic pump would normally be off unless the pipe starts stretching, and then it squirts a little bit of water in. But we can see the pressure here, and we monitored the pressure throughout the whole test, and we monitored the status of the pump through the whole test, and we verified that the test was done properly. In addition to that, we also wanted to verify that the system didn't get damaged during backfill. So what we did is we just left that system in place. We left the pressure transducer and the hydrostatic pump and the pressure switch all in place, and we monitored it from our cell phone, literally. Sitting here in Macon, Georgia, we monitored this project was in Albany, Georgia, and so we can see our pressure was holding steady, and it would drop sometimes when the pipe contracted, or when the pipe expanded. Actually, the pressure would drop, and when the pipe contracted, the pressure would go up. But our pump is off, so we're not worried. Then all of a sudden, one day, the pressure bottoms out, and the pump starts cycling. And it cycles and it cycles. And so we called the contractor and we said, hey, we think we got a leak. And the contractor said, no way, we hadn't nicked anything. But we shut it down right here and we started investigating. And sure enough, they had nicked the pipe with a bulldozer or a backhoe or something. And we were able to get that fixed before it was covered up and nobody knew about it for a few years. That would have been bad. But we were able to figure that problem out before it became a problem later on. Verifying performance makes problem solving easy. That's what the commissioning guy does. He verifies performance of the systems. And in this particular job, we found this problem. This is a three-way control valve that was installed backwards, and this is a hard thing sometimes to figure out what's going on. But when we were measuring the performance of the water-to-water heat pump, there was times when we just didn't have. It was tripping out. It was like we didn't have any flow rate. Well, guess what? We really didn't have any flow rate because this valve was installed backwards. And I hope you can see this on your screen, that this valve has an A port, a B port, and a C port. And this is the correct orientation. This is not a correct orientation. Our C port is here, and our A port is here, and our B port is here. So this valve closes to A or it closes to B, but it never closes to C. It's what's called a mixing control valve in this application. So there will be times when A is closed that the pump doesn't get any flow whatsoever. But over here in this orientation, when you put C on this side, now we either get all A, or we get all B, or we get a mixture of the two. And this happens. This setup is for a water-to-water heat pump. Typically, they can't receive water any hotter than like 70 degrees in the heating mode. And the way we this is our loop over here. The way we fix that problem is we just put this mixing valve. So if this water ever gets hotter than 70 degrees, we just shunt some of this colder water, 60 degrees or 55 degree water here, and it mixes in with our hotter water, and we get the water temperature that we need to the water-to-water heat pump. And now I'm going to turn this section over to Chuck.
Thank you, Brandon. I appreciate everything you said. For the record now, we weren't fracking anything Literally, that's just a big open tank that's used in that industry, but it also works well when you're doing these really large flush and purge jobs, because you can imagine, if you do the math, 4 feet a second through an 8-inch pipe is a lot of flow. So you usually have an engine-driven pump, and you got a couple of tanks out there that you're sending the flow through, as Brandon said, to get the beer cans and the mud and the air and everything out of the system. And can't emphasize how important that is. If you do have a manifold chambers underground, then it becomes easier to isolate the sub mains. But anyway, that we've really gotten all those things worked out over the years. Each engineering firm has their way of doing things, but we try to emphasize the commissioning and the tab work, and especially with the geothermal type projects, because they're a little unique and contractors aren't used to dealing with them. All right, so I'm going to talk about HDPE welds, and I'm going to talk about some of the stuff we do out in the field to try to ensure the integrity of these systems. So I'm going to start with the types of fittings that you have. The key thing with the HDPE pipe is in my opinion, that you weld it. There's some systems that are at higher temperature, and you have to use PEX on that, or if some of you saw the UTIS E seminar we did last month, which is high temperature storage between 250 and maybe 500 degrees Fahrenheit for high temp thermal storage purposes, or even electrical production, then you have to go to metal tubing. But the vast majority of all geothermal heat pump systems are constructed of high density polyethylene. It's a great material. That's what gas goes through, unless it's at really high pressure, so they don't have to worry about cathodes and anodes and corrosion. Most of your fiber optics are routed through HDPE. So in the black version you see here, that's typically potable water. HDPE is used for drainage also. But in the context of geothermal heat pump systems, we personally like the double rollback joint that you see on the left here, which is a butt fusion joint right there. And at first, I didn't like those. You look at these socket fittings, and if you've ever been involved in high pressure work like hydraulics, oftentimes you get up into thousands of psi. You have socket welded fittings. But the problem with the socket welded fittings is that you can't really see the weld visually to observe it. And we're not using x-rays or anything else to determine these joints. It's more of a field inspection. So we're not a big fan of socket fusion, although you may have to do it on occasion for transitions. Really small pipe, you might have to do it. And another type of fitting that's used sometimes in geothermal industry is down here. This is sometimes called electrofusion. The fitting literally has two electrical connections here. And if you can see there's some heating elements in here. And so you literally heat up the fitting there by hooking it to a machine. It's nice because it's low. As long as the people in the field get the fitting clean, then it does apply the exact amount of heat, and you can log it with the machine, and it can give you a full record, even with GPS coordinates of where they are. But these joints are very expensive, so you don't. They're kind of a specialty thing you see for retrofit and other work, but most geothermal heat pump systems use a butt well. And the beauty of the butt well is, as you can see here, you're basically taking a specialized machine and you're heating up the face of one pipe and then the other pipe to get them soft to a certain discrete temperature point. And then you push those two pipes together. And I know it's a little bit hard to see in here, but it represents a cut through the pipe. And you basically end up with the material thickness in here being it looks like the bottom part of this got covered up a little bit, but the material being almost twice as thick as at the joint as it is elsewhere. So the proper joint is on the left. You got these two rollbacks there where the polyethylene literally rolled backwards. And then when you take a saw and cut it through here, this gray area is the cross-sectional cut. And you can see that the joint is actually thicker than the nominal pipe. And most of the time, if you put this in a test stand and pull on it, it will actually fail somewhere other than the joint, because the joint is sometimes as much as twice as thick. So if you get a nice, pretty joint like that, you know visually that very unlikely you're going to have a leak. If you see crap like this where the two pipes are misaligned, as you can see there, then you've got a joint that oftentimes is not going to hold. And it's kind of, I'm sorry, that picture's a little bit small, but there's another screwed up joint there. So we like butt fusion because you can visually inspect the system and ensure that you get a nice well there. So that we recommend really butt fusion. You can butt fuse huge pipes, pretty much everything you would ever use in a geothermal system with some specialized equipment. What are some other things we do to try to ensure the integrity of the system? We like to use the U-bends that we've talked about before that go down into the ground that are in essence the heat exchanger that's pulling heat into or out of the earth. We like to buy those that are have Schrader valves pre-installed on there and are pre-charged with air. So there's a certain charge. They come from the factory, and if you've had to sit through a fluids class or physics, you know that the temperature and pressure vary with a gas. As the temperature goes up, the pressure goes up. So the pressure will vary some amongst here, but you have them shipped from the factory at a certain charge. You hook basically a pressure gauge like you'd use on your tires of your vehicle up to that, see if there's still pressure in there. If there's not pressure in there, then you pump it up and see if it holds and somebody just had let the air out, or if it's got a leak, and you cut the leaking section of the pipe out or replace the U-bend before it ever gets anywhere near the ground. And then we like to, after those are inserted into the ground, we like to leave those two ends sticking up 3 or 4 feet above the ground and come back periodically and check the pressures in there to make sure they haven't fallen off. Either the commissioning agent or the contractor makes a log of each of those and testifies that all the U-bends are still good. And then we header everything together. And as Brandon showed in the other slides, we like to install live pressure monitoring. And it is a little tricky with HDPE, as Brandon alluded to. We observed at the BTES system at the Marine Corps base in Albany, that was the source of some of these slides here, that as the sun heats the pipe up during the day, the pipe grows faster than the water grows, and so the pressure drops and it cools down at night and the piping contracts, and you start to see these diurnal cycles that are not indicative of a leak. And if you're also monitoring, as Brandon mentioned with the hydrostatic pump there, how much flow you're letting in, then you know whether you're net continuing to add water. And after a certain period of time, you should not have to add any water in there. But HDPE piping does stretch. And so you've got to take that into account, that you will need to put water on it for a while. The actual ASTM pressure test is only about a 4-hour test. And so you pump it up, you back the pressure off a little bit to stop the stretch, and then you monitor it for a short period of time. And we do that test for sure, but we also like to just continually monitor it before backfill started. Because like Brandon said, when you saw that big plummet in pressure, we actually called the contractor, Brandon and I and Joey, we all had this on our iPhones, so we got an alert, called them immediately. They went out when they found the leak and found the nice wet spot in the Georgia clay there and knew exactly where it was. And so it took them a few days to get it fixed, but in the end, it turned out to be a very beneficial thing. So we like live pressure monitoring during all backfill procedures. We also like to We trust contractors, but as Ronald Reagan said, trust but verify. So we actually have a tagline that we use because we're involved sometimes in the drilling operation. This is a spool, and it has markings on the wiring, and then it has a tag, which is essentially a stainless steel weight. It's about 1 foot long and maybe 3/4 inch in diameter. If you don't have one of those, we use actual data loggers. When we do thermal conductivity testing, we actually drop temperature loggers down into the ground and measure the temperature underground at various depths, as we're trying to determine what the deep earth temperature is, because it varies with depth. But anyway, you drop one of these suckers down into the one end of the U-bend after you've completed the initial pressure testing of those and cut those Schrader valves off I showed you earlier. And we like to verify what the length of the at least a representative number of U-bends to make sure we're not getting short looped, because regrettably, occasionally you will have contractors that short loop you. One way you can kind of avoid that, and that's on this piece of pipe down here, and I know these numbers are hard to read, but one of the things that's stated in the on the side of the pipe is often the length of the pipe. And if it's a big roll of a pipe you're using for headering, it doesn't matter. But for U-bends, you can have the length printed on the U-bend, typically, what is it, Brandon, every 2 or 3 feet or so. And unless the contractor gets really creative and hacks out a section of the U-bend before he puts it down the hole, you can read the length of the pipe off the pigtails sticking out of the ground and know what length it is. And we think that's an important parameter. Another parameter that's typically printed is the manufacturing location, and HDP is pretty. It's still made in America, and it's kind of expensive to ship for a low-value product. So you don't get a lot of foreign piping in here in plastic like you do with steel. But if you require domestic manufacturer, then the manufacturing location is stamped on there. And then also the polymer mixture that you require, and 4710 is what's usually required today. And so the PE resin that's on there is important too. And then also you usually require an NSF certification, National Sanitation Foundation, sometimes American Water Works, but always an ASTM number on here. It's important to see that that's there. And then the thickness of the pipe that you specified. The thicker the pipe, obviously the more robust it is, but the crappier the heat transfer is. Sometimes on really deep wells, you might go as thick as SDR, standard dimension ratio of 9, which means that the thickness of the pipe is roughly 1/9 of the diameter of the pipe. But SDR 11 is more appropriate, and occasionally you can get to thinner pipe, even like SDR 13.5. But SDR 11 typically is rated at 200 psi, and so you see that stamped on the side. So we think it's very important to look for those parameters when you're out in the field inspecting the pipe for commissioning purposes. All right, so how do we eliminate, how do we find, and how do we repair the leaks? Obviously, the best medicine is preventive medicine here. So all these things we've talked about in the first place, where you're working really hard to make sure long before the system is put into operation that there are no leaks in there. It's a little bit different than steel welding. You can have ASME certified welders for various applications, but when it comes to welding plastic, people are typically certified by the welding company manufacturer. They'll have a protocol you go through. A little bit hard to see here, but this machine is a tracked machine that might be out in the field. There's a disc here with blades on it where you're trying to get a true face on the face of the piping, and these can be huge pipes, up to several feet in diameter. But most geo applications are typically under 12 inch, all the way down to. We don't go any smaller than 1.25 inches. On some small systems, you might go inch or 3/4 of an inch. But anyway, there's a series of heated plates here that melt the ends, and also to apply the proper pressure at that joint, these machines can load the piping axially so that it smashes the two melted ends together. And it's important that you get people who know what they're doing in the welding. But if you do, these are welded systems buried underground. They're not subject to corrosion, UV rot, or any of that. They can last you for decades, if not indefinitely. Another tool that may scare you to death when you first see it is a pinch-off tool. If you're in a place where there's not a manifold chamber or a good way to valve off this, you can actually pinch off the flow to that area, work on it, and open it back up. And you think you're destroying the pipe. But in general, the manufacturers approve this protocol as long as you use the right machine. You don't apply too much pressure. Obviously, you want a nice curved surface there doing the pinching. But that allows you to isolate the piping live while you work on it. And if there's a leak and you don't have a manifold chamber where you can isolate a section, that's a tool you have to use sometimes. But what happens if there is a leak? Leak detection is tricky, that's for sure. If you've got these manifolds that Brandon talked about earlier and these big underground vaults, you can isolate it circuit by circuit by circuit until that pressure transducer that we talked about before, or that hydrostatic pump, does not need any makeup anymore. And at that point, you know which of the branch lines. On our BTES systems, we typically only have 3 zones, so there's only 3 boreholes per circuit. But on a conventional geothermal system, you might have dozens of boreholes per circuit. But in any event, you want to first isolate it down to the circuit that is leaking. And then what kind of techniques do you use to find it? We have even heard of crazy things like one contractor said he knew of someone who would grind up animals, cadavers, and then inject that into the system and let it pump out 10 or 15 gallons of that nastiness, let the bloodhounds smell it, and then go out there and find the leak. We don't know whether that's a wives' tale or real. We've never tried that, but the two-star general at Albany, we had one leak there, and we found it using the methodology of being able to pinch off the branch circuit, isolate it, and then get rid of the leak. But we were pretty happy that out of miles and miles of piping and 306 boreholes that we only found one leak after the system was made operational. But there's also some people who have talked about using thermal methodologies where you put as warm a water through the HDPE as you can stand it, and then to thermally scan the ground. The problem with that is the sun's rising and falling, and the ground and the earth is heating at different rates. So you might have some success with that, but acoustical leak detection is legit. I was talking literally today with a contractor who kind of specializes in this. They have been called in on a dozen projects, and the key thing he said to finding the underground leaks acoustically is to have a good set of as-built drawings where you actually could literally come out on the ground and spray out the loop that's leaking. So, the idea is you go to the manifold chamber, you find out which of the loops are leaking. Then once that's established, you look at the as-built drawings, which are rare sometimes, but as-built drawings should have some key dimensions off of the building and so forth. They spray the outline. It could be on the top of a parking lot. A lot of times these geo loops are put underneath the parking lot. He said, you can be under concrete or pavement or just under grass. They basically, he said, out of all the dozen or so times they've done it, that probe you see the guy holding in his right hand is a probe that can actually go underground, but you can also set the transducer on the ground. And he said only one time, even with parking lots, have they had to actually drill through the pavement and put the microphone underground. But in essence, the key techniques to use with that are to isolate it down to the circuit that you've got there. Attach, in addition to the water makeup, you attach a high volume, low pressure air compressor and mix air in there with it so that you end up not just water spraying into the dirt or not just air hissing out, but a gurgling, kind of a violent situation there at the leak where water and air are both gurgling out at the same time. And they basically go along the markings on the ground until the noise hits the highest level and then dig down and found the loops. And, he said they have found that 12 out of 12 times. So, we're a little skeptical about that, but we have talked to geothermal contractors that specialize in that. And usually the geothermal contractor may not have the acoustical equipment. They bring in a leak specialist. The particular contractor I talked to today from New Jersey, they had a couple of different leak detection companies that they work with, and they come out there with them and assist it. So, hopefully you'll never have to deal with that, but if you do, at least there are potentially some techniques you can use to try to locate it. So we are completed our slides now, and I'm going to take this out of the laser pointer view. Stop, Joey. Thank you. I'm going to take it out of the laser pointer view, and then now you can have it, Joey. So we're going to open it up to questions. As you know, we've asked for people to submit those questions via chat. So it looks like there's 2 or 3 questions in here. So I'm going to go down through those questions. I'll let Brandon take the first one. The question is, how close to the 2 PSI do you recommend the pressure differential should get? So I think, Brandon, specifically, I think they're probably referring to the fact that the automatic flow control valves, we showed that they had an operating range of 2 to 32 pounds, but we probably need to go, I don't know if we can go back to that slide, that's probably too complicated, but the differential pressure transmitter is kind of covering, yeah. You want to do it, Joey, or me? Okay, all right.
Yep. Yeah. So that's a good question, and I don't think that you need to go down to 2 psi.
Yeah.
I mean, the problem is that once you get down to 2 psi, your valve's wide open, and you don't really know if it's receiving you don't know if it's receiving design flow or if it's receiving less than design flow. So when we balance a system with automatic flow control, go back one more slide, Chuck, please. Yep, that's it. So when we balance a system with automatic flow control valves, the most remote valve, we will not try to hit quite 2 psi, maybe like 3 psi or something, and that's very close. I mean, that's getting you pretty close to your minimum pump speed for that particular scenario.
So said another way, we've got to keep at least 2 pounds, somewhere between 2 pounds and 32 pounds, as Brandon indicates here. That's for that valve to truly control the flow at whatever design set point is. It needs a differential pressure between 2 and 32. But the differential pressure sensor, and sometimes there's multiple ones, but a rule of thumb is 2/3 of the way down the piping hydraulically. So the differential pressure here is going to be higher than 2 pounds. But what would you say, Brandon, the typical range we've encountered over the years, chill water, hot water?
For the differential pressure sensor?
Set point.
Yeah, I'm going to just pick a number 10.
10
PSI.
Yeah. So we're talking about a differential pressure of maybe 10 PSI. At that pressure transducer, then there's PD through this pipe, and there's PD through the water source heat pump, and then we need to have at least 2 pounds difference across there. But we're just trying to get an average reading, so that's why this differential pressure is connected between these two mains right here, trying to make everybody happy down through there. And as Brandon mentioned before, with dynamic set point adjustment, we can keep backing that down as low as possible.
On systems that don't have automatic flow control. I mean, this is water source heat pump 2-position control valves. Yes, I agree. The problem is with the automatic flow control valves is that the control system doesn't know whether they're fully open or fully closed. So I will say that dynamic reset doesn't work very well with automatic flow control valves, whereas I said that a little bit wrong. With the 2-position control valves, right? They're not modulating. Mm-hmm. Whereas on the modulating control valves, the control system has something to look at to see which ones are open, which ones are closed, or which ones are in between.
Yeah. So get more specific with that. As Brandon says, if there is a 2-position modulating valve there, possibly on the chill water side or the hot water side, then and that's a smart valve that's communicating its position back to the central controller, and it says, "Hey, I'm half open or I'm 2/3 open." You got to have that piece of information.
Well, you don't. It doesn't necessarily have to send the signal back, but if you know you're sending at 100% signal, you're just assuming is 100% open.
Yeah, right.
Yeah, it doesn't necessarily.
It's not necessarily a direct feedback, but whatever position you've told that valve to go through. And so
that's right.
All right, so let me hit the next one. What is the difference between tabbing a conventional open loop geo system versus an ATIS system, or a conventional closed loop versus BTES? What I'd like to say in regards to that is that what we like to call a BTES system is just a closed loop system on steroids, and an open loop system on steroids is ATIS. So what does that even mean? Well, in conventional closed loop geothermal systems, you've got a ground loop heat exchanger out there. All the boreholes are piped in parallel, so you can't really differentiate between an interior borehole that might be good for storage or an exterior borehole that's maybe better for dissipating heat or extracting heat. So with BTES, what we try to do is we try to stratify that core, really kind of going back to the slide. And I would encourage you to go to Whole Building Design Guideline if you want to learn. Well, here's a good picture of it. If you want to learn more about how these systems work, I would encourage you to go to Whole Building Design Guideline, www.wbdg.org. That's the federal website that has all the federal specs on there and all the facility criteria. And if you'll go underneath continuing education and DOD, you'll find the original UTIS, Underground Thermal Energy Storage webinar we did back in May. and then there's an ATIS specialty seminar and a BTES. And then, and all three of those are up and now available on demand with PDH and AIA hours if you need them. But, looking at this illustration here, this represents a BTES and the fact that we're trying to have the coldest in the core and warmest around the perimeter, and we're trying to store cold. So with a BTES system, you do have reversing valves that allow you to reverse the flow. And then we almost always have an active means, in this case, storing cold, of heat rejection that we're operating. So what we have to do with a BTES that we don't have to do with a conventional closed loop system is we have to decide when we're going to reverse and when we're not going to reverse. And we're also trying to balance the heat on the ground on an annual basis. So we have to make the decisions of when to operate the dry coolers and when not to. So those are some control sequences that you don't normally see, and it's important. Hopefully the engineer specified what had to happen, but it's definitely imperative that the commissioning agent get in there, look at those sequences, make sure we're actually running the dry coolers hard enough, and making a logical decision on when we're charging and discharging. Would you say,
That's
Brandon?
right, yeah.
And on the open loop systems, ATIS, a traditional closed loop system will have dedicated supply wells and then dedicated injection wells that will have ideally the injection valve like we showed, because you want to keep back pressure on the system at all time, and you really have to put that valve at the bottom of the injection pipe down deep underwater. We don't want to mix oxic water with anoxic water. We don't want to get oxygen in the system. Some critical things there are to keep those systems where they're under pressure and you're not mixing water flow, and those injection valves are operating properly. As Brandon alluded to, we've had a couple of problems where we weren't getting even flow through the injection wells. It wasn't a problem that impacted the system being able to operate. It just, we want to squeeze every ounce of energy savings out of there. So the more we can balance the flow between the ATIS wells, and we figured out how to do that now with those injection valves, the better off we are, because the more we spread the water out amongst the injection wells, the less mounding we have. And so the less mounding we have, the less work the pump has to do. So those are a couple of critical things to me, is getting those unique sequence of controls done and making sure that they're operating like they're supposed to. And I think one of the other things that's weird about ATIS and BTES is people are used to seeing cooling towers running wide open in the summertime. I mean, it's hot, you got to reject heat. We don't do that with geothermal in general, but certainly ATIS and BTES systems. We want to put that heat down in the ground. It's too hot outside. It's going to be too much work to dump that heat to the air. So then when it gets cooler outside at night, now we're going to crank up the dry cooler. Or even in the dead of winter, people come around and go, oh, the system's screwed up. It's 25 degrees outside and the dry cooler's wide open. We go, yep, summer's coming. We're trying to make cold all winter long, because the vast majority of our projects are all highly cooling dominated. So we want to make hay while the sun isn't shining and get that cold. So it's a different way of thinking and commissioning to have these systems that are storing cold in the winter, and if you need it, storing heat in the summer. So those are kind of a little bit different about those. All right, so problems that we've encountered, we kind of alluded to some of those, like them cutting the pipe and us sitting there monitoring it live. I would say another issue is we're very greedy with energy, so we like to use heat recovery chillers. We don't. Almost every building we've been in has more than enough heat internally on an annual basis to satisfy any of the heating loads. So we like to use heat recovery chillers, and I kind of consider geothermal as the enabling technology that you hook to these heat recovery chillers so that they can cool or heat, or ideally do both at the same time. Make the hot water for the VAV boxes for reheat or space heat simultaneously, but they're going to be cycling on and off all the time if they don't have some place to dump the excess heat or the excess cold, and that's where the geothermal system comes in. So I think geothermal heat pumps with heat recovery, unless you're in a hospital or something with a big base load, you need the geothermal to keep the heat recovery chillers stable. And even then, you need the factory people there, and you need a commissioning agent like Brandon that cares and sits in there and works that sequence to death until you get those chillers where they're behaving. You got any comments on how to make those chillers?
Yeah, I mean, the chiller is a big part of it. Also, I mean, the rest of the sequence of operation is a big part of it, especially the dry coolers like you were talking about before. And I mean, they're just, to hit on a few other issues that we've had in the past is a lot of construction issues. Through-way valves, like I had in the picture, not oriented correctly or things not piped correctly. Pumps operating in reverse, particularly submersible pumps, that can happen very easily because you can't look at the pump to see which way it's turning.
Yeah.
You got to put your amp meter on it, your flow meter on it, and see if it's where it's supposed to be. And if it's only doing half of what it's supposed to do, then you must be running in reverse. We've seen issues with HDPE welding, and just the sequence of operation in general. I mean, controls. In the commissioning world, controls are our biggest problem. A lot of times, and so you just want to make sure that stuff gets programmed correctly and is operating right.
I think Brandon may have touched on it before. I can't remember, but in general, VFDs, from an energy standpoint, you want to drive the fan or the pump or whatever to the lowest possible speed. Depending on the manufacturer, that pump or that fan, they may tell you 25% or 30% or 33%, but just be aware if you're using open loop Geo or ATIS system, submersible pumps typically have a water-cooled bearing on the bottom of those, and pretty much every submersible pump manufacturer, we love submersible pumps. The pumps are water-cooled, they're deep out in the underground and pristine groundwater, and they can last a long time. But you do not want to drop the speed of those below 50% because at that point that essentially it's a journal bearing down there is water lubricated, so you got to keep it at least 50%. So put lots of pumps in there, and then you can still stage down as Brandon had in his slide. The system we've currently designed at the Naval Air Station Pensacola, we have 3 cold pumps and 3 warm pumps. So at any time, if we get down to minimum load, which we can, then instead of 3 supply pumps, we only got 1, and then we've cut it down to half. So we got, we're down to 1/6 of the capacity. So we got a 6-to-1 turn down, and we can live with that. But if you just had one big humongous pump in there, you'd be stuck at 50% turn down. So that is kind of a unique thing about the closed loop systems.
Open loop.
I'm sorry, the open loop systems. Thank you. Thanks for the comprehensive presentation. I'd like to learn about the cost of BTES systems. Thanks. So I would say a couple of things. If you're used to using closed loop Geo, then the BTES system is going to be analogous to closed loop Geo with a couple of other things layered on top. You've got to have these reversing valves that allow you to go from the core to the perimeter. And the bigger the tonnage, the less of a factor those become. But probably the smallest system we've done with BTES, Brandon, what was that, 67 boreholes maybe? I think I counted them up the other day. And what was it roughly, 75 tons?
Roughly, yeah. 75
is less than 100 tons. We kind of say minimum tonnage for a geothermal system to be done BTES is probably around 75 tons. That's because you've got to buy the reversing valves. And then the other thing is obviously circuiting the boreholes is a little bit different. But the contractors we've worked with have figured that out pretty well. If you give them a good set of drawings, and we lay out the boreholes just like you would do a structural plan where you've got columns A, B, C, D, E, F going one way and 1 through 50 going the other way. We label each of those boreholes and give you a grid to lay it out on. But the unique part about the excavation is instead of digging a bunch of ditches with a backhoe, when we do BTES, just to make it easy, we do essentially, like we call it a pond excavation. You go down maybe 4 feet, take the dirt completely out of the way, do your job on a flat surface there, get it all back together, and then backfill on top of it. So you've got some additional backfilling cost there that would be more than the ditch cost. And then I guess the only other thing is we generally like to use dry coolers because they work better in the dead of winter than a cooling tower does. So if you don't have to go that way, you can go cooling tower, but dry coolers generally do better in the winter than cooling towers. And we kind of hedge our bets and do evaporative cooling on the inlet to the dry coolers. We call that an adiabatic, or some people call it a hybrid dry cooler, where we live in Georgia, so we got plenty of chicken houses around here with that evaporative pad on one end of the chicken house. It's made out of cellulose, and so we like that as opposed to a cooling tower that has PVC fill. So we treat that cellulose evaporative pad as a disposable, and we don't have to deal with Legionella and water treatment and all of that stuff. It's a once-through system where we evaporatively cool the air coming into the dry cooler if we need to. And when the pad, and we try to not run much water through there than what's going to evaporate. So, yeah, eventually the pads clog up, magnesium and calcium, but then we just chunk them just like you would an air filter. So at the end of the day, I don't know what the premium is for a BTES system. I would say it varies by tonnage. If you're a really small tonnage, really small, like below 50 tons, you might double it. If you get really large, maybe a 10% premium. So that's about the best I can give you for hard numbers right now. I think at the Marine Corps Logistics Base, that huge 306 borehole system with the excavation and the boreholes and the circuiting, all of that, I think it was about $1.5 million maybe that we spent on that. So that was roughly a 425 ton peak capacity system. We spent about $1.5 million outside. I think that included the dry coolers too, as I recall. But anything else you want to say on that?
No, I'm
all right,
good.
Let's see. We got another 9 minutes, so let's hit them. Yeah, Lewis comes back and goes, yeah, the 3 PSI at the farther circuit with those 2 to 32 PSI valves is what I also recommend. Good to get reaffirmation.
Yeah, I agree. I don't recommend going down to that 2 on that last circuit. So
Yeah.
that's a good call.
Yeah, and let's see. I'd also like to learn more about the economics of these systems. So yeah, if you really want to do the deep dive, if you don't mind, y'all should have our email addresses in the invite you got. But if you can address an email to C Hammock. In fact, let's go to that last slide. I'll go to it, or you can do it. I got it. So I think Brandon and I both have our there's our emails there. Just email me or Brandon, and we'll give you a link to the DoD website where the final report is on both of the BTES and the ATIS demonstration projects, and you can see what the cost information is there on that. We are currently designing an ATIS system that will be implemented under something called a Utility Energy Service Contract, or UESC. So the government procures energy savings projects under several different vehicles. One of them is called an ESPC, and another one is called a UESC. So the ATIS system we're presently doing at Pensacola is procured under a UESC contract, and we have another ATIS project underway right now that is being done. The one at NASP is being done in conjunction with Gulf Power, who is owned by Florida Power and Light's parent company, NextEra. And then we've got another project with Dominion Energy up in Virginia, where we are a little bit colder geology, cooler climate, longer winters. So we're actually going to store that chill water down to maybe 45 degrees in the wintertime and actually run the system without the compressors. But when those projects get finished, that cost information will be available. And if anybody here is federal or even private sector, ESPC projects, or something similar to that is done in the private sector, where another acronym is ESCOs, energy saving companies can go in and do in a private sector a project like geothermal or LED lighting, change out, that kind of stuff. But our next webinar, and really the last one, the 6th one in this series of 6 webinars, will be held late spring, where we will talk more in depth about the Dominion project and the Gulf Power project and the financials and how that worked out through something called the PA, the preliminary audit process, and then the stage we're in right now is called the IGA, investment grade audit. So there'll be quite a bit of financial information available ultimately on both of those projects. But shoot us an email, and we will we'll send you a link to the ESTCP website where you can enjoy the, what is it, Brandon? 750 page. How long is the final report?
Yeah,
for the original
it's
ESTCP
long.
project?
It's long.
Anyway, you can enjoy our final report in all its glory if you're interested. All right, let's see if we got any more. Yeah, that was the economics. I think we've hit all the questions that were there. We appreciate you guys joining us, and hope you learned something. Hope something was helpful, and we'll see you back again maybe in May. And go ahead. Yeah, PDH.
Yeah, I did want to just mention the PDHs again. So if you go back to the email, to the registration email that you were sent when you registered, there's a link on that email. And that link will take you to our website, to utishub.com, and there should be a link to take a survey. After you take the survey, you'll be automatically sent a PDH. If for some reason you have an issue doing that, please reach out to me or Chuck or Joey by email, and we'll be happy to send you a PDH manually. So.
And if you're DOD or federal, sometimes they block the UTES, www.uteshub.com website. So